All right, so really quickly, I want to just sort of go over a different idea, a different model for uh, how you might want to think about instructions going through the pipeline. And this might just be a bit helpful, depending on whether or not you have a solid grasp of what's going on. So if you think about, so I'll have sort of my stages here. So this right here is essentially just saying I'm waiting to get into this next stage. So this might be stage number 1, and the output here would stop here. And I sort of drew this picture before, but yeah, the idea, this is essentially one of the ways that you can think of a pipeline. You have the input to the pipeline, and then it sort of gets stored in these temporary buffers as things progress through the pipeline. And I'll just go ahead and do, let's say 3, or I'll do 4 stages, sure. And I'll leave that like that. Okay, so you can sort of think like an instruction can be at one of these locations at a time, and then when you perform a cycle, the instruction can either stay in this unit here, or it can move through the actual pipeline unit and stop at the next one. And so what's going on here is essentially the process that we've been talking about. However, you want to think about where the instruction is. So just for instance, if instruction 1, or I guess, let me recall these units by letters to make it less confusing. So that's just be unit A, unit B, unit C, and unit D. So let's say instruction 1 starts, and it's here. And then it processes through A, and then it's over here. And then it processes through B, and then it's over here, and so on. Then instruction 2 starts. So let's say instruction 2 starts immediately after 1. So that means that we have instruction 2 right here, and instruction 1 right here. And let's say during A, that's when the instruction is fetched and decoded. And we'll say that instruction 2 here, it needs to use, let's say, unit C next. So it doesn't really need to do anything. And we can say that it's allowed to jump over if it needs to. So what happens the next cycle is 2 needs to use this unit next. However, it can't do that, right? Instruction 2 would have to use unit A first. So let's progress a cycle. So unit 1 will go over here. Instruction 2 will go over here. Now unit 2 wants to use unit C next, right? It doesn't need to use unit B. And so you would have wanted to basically move 2 all the way up to here. However, 1's here. So you can't do that. So 2 is going to just have to wait somewhere in an internal buffer. Then it'll progress. 1 will pass through unit C and come over here. 2, however, will just jump over unit B. And it'll just sit here, waiting to use C, right? We just used C for 1, and now we're waiting to use 2 for it. And then we progress forward. 1 would get finished executing. 2 would go ahead and use unit C. And then maybe on the next cycle, it uses D or not. It doesn't really matter. But let's draw this out how we've been normally drawing this out. So if I have my unit A, B, C, and D. So I'm assuming here that instruction 1 just has to use every single unit. Instruction 2 uses unit A. Maybe that's the fetch and decode, which it has to do. And then only unit C. So how does that get executed? And what happens with something coming behind it? So let's see here. So let's say we start by instruction 1. It just goes here, and then it's going to progress over to here, then over to here, and then over to here. Well, instruction 2 is going to be waiting to use C. So it's going to use A, or sorry, that should be a 2. So it's going to use A, then it's going to be waiting, and then it's going to go ahead and use C, and then it can be done. If we're now, let's say, using instruction C, or actually, what would be better is, let's say we have this situation. So we use 2 here, and now there's a data dependency. So we have to wait to execute 2 in unit B for some reason. Do we want to start instruction 3 here? Does that make any sense? Well, let's look at this example here. So we start instruction 1 in A, right? That's what that's telling us. At this first timestamp, instruction 1 is just going to execute in A. So it's going to pass through here, progress to here, right? So now we have instruction 2 here and instruction 1 here, right? That it represents this timestamp. Well, now 2 has to wait. It can't use B just yet. So I mean, here really at this point we're right on this line right here, right? Because we haven't done 2 in A and we haven't done 1 in B, but we're essentially waiting to do. We're just about to do that. We're ready to do it. So we can go ahead and do that. So everything's going to progress forward by 1. 2 is going to progress forward by 1 over here. So now we need to wait for 2 to use B. So what happens? Well, interleaving I'll get to. Interleaving has nothing to do with pipelining. Interleaving has to do with how the memory is organized and how that affects how things can get scheduled in the pipelining. Pipelines cannot be interleaved. Memory is interleaved. I'll get to that later though. Just assume here that interleaving doesn't matter. So here we draw that 2 sort of skips over and it has this gap. But really 2 is going to be waiting somewhere. 2 has to be waiting, let's say right here. So that's at this timestamp right here. So even though 2 doesn't appear anywhere, it's still going to be sitting here. So now if we started instruction 3, right, if we also said, oh, we're going to start instruction 3, that means 3 would be right here. And so when we say, okay, go ahead and progress, well, 2 has to wait here because it's waiting to use unit B. So 1's going to move forward, 2 is going to stay here, and 3 has to stay here because it can't get processed by A and then move on to this stage because 2 is taking it up. So there's absolutely no point in scheduling 3 right here because it doesn't have any room to progress in through the pipeline. 3 cannot start right here. So 3 actually has to wait and start here. So now, once we're in this position here, right, so at this timestamp here, we'll start instruction 3 here. So now we have 1 about to execute in unit D, 2 about to execute in unit B, and 3 about to execute in unit A. Then once we go ahead and clock the cycle, 1 is going to progress forward, 2 is going to use unit B and come over here, and 3 is going to use unit A and come over here. And then we're at this time step here. So here we can't start 3 early because there's no room in the pipeline for that instruction to be somewhere. Well, again, so back at this time step right here, we have one waiting to use one waiting to use unit C, and 2 is sitting right here, right? Because so at this time step here, let me just back up to this moment here. So at this moment here, right on this line, we have 1 about to execute in B and 2 about to execute in A. So it goes ahead and does that. So we go ahead and execute these instructions, and everything moves forward by 1, right? But now, what we're saying is after we've done unit A, we've discovered that 2 has a dependency on 1 executing in C, but it needs to use unit B. So essentially, we have, let me pull out some color. So we have that this unit here has to happen after this unit in time. So here, 2 is going to wait. 2 has to wait to be able to use B. And so when we do a clock cycle, the CPU isn't going to go ahead and execute 2 because it can't. It needs to wait to be able to do that. What it's instead going to do is it's just going to execute 1 forward and come over here. Right? But 2 is going to stay here because it needs to wait to use that instruction. And we can look at some example. We'll look at some examples later with the actual instructions so that it might maybe be more clear. But we're just assuming here that there's a data dependency right here. So 1 goes ahead and moves forward, and 2 stays right here. And so if we would have said, oh, at the beginning of this cycle right here, we're going to go ahead and start instruction 3 in unit A. Well, it doesn't have any room to store the result because 2 is blocking it. 2 is taking up that room in the pipeline. So we can't start instruction number 3. And so you don't want to start 3 right there. That wouldn't work. Does that answer your question? And if not, that's fine. This is definitely the most complicated part of pipelining to get a grasp on, is just you want to think about things moving forward 1 unit at a time if they can't. If they have to wait at some point, then you can't just start scheduling stuff up behind it, right? There has to be room for that instruction to be held. Oh, but I'm saying that, so at this timestamp here, so this is answering Justin's question. So at this timestamp right here, we just finished executing 2 in A. So 2 is now right here. We just finished executing 1 in B. So now 1's waiting right here. So if we decided to also start number 3, right, that would indicate putting a 3 here. And we set, when you execute, right, things either have to stay in this unit or progress through the next, or progress and go into this next thing, right? The instruction has to be stored at one of these locations. Otherwise, it's not in the pipeline. If it's not somewhere here, it's not going to get executed. And so at this moment here, at this moment, 2 has to wait. We already know 2 has to wait. It can't execute in B immediately. So 2 is going to stay right here. So when we go ahead and do a clock cycle, 1 moves forward because it's fine. It can just execute in unit C. 2 can't, and 3 can't execute in unit A. So it's invalid. It's wrong to put a 3 here because 3 didn't actually execute in the A unit right here. Does that answer your question? Justin specifically? So like right now, the state of this pipeline here is right here. So now we can put a 3 here because during the next cycle, 2 can now run in B. So 2 is going to run in B and progress forward. 1's going to run in D and then it's out. And then 3 is going to run in A and progress forward. So now everything's going to just move forward 1 step, and that's fine, right? If the thing ahead of you is moving forward in the line, you can move forward in the line as well. But if the person in front of you, if the instruction in front of you is sitting somewhere waiting for something to happen, you can't just skip in front of them. You have to be behind them. Okay, next question. So when 2 different numbers are diagonal from each other, like that, it's a clue. Well, so here I'm just saying that this is an arbitrary data dependency. Normally, like the goal here is for you to give this as an answer. Like we would give a sequence of instructions, and then you would have to give this. Yeah, let me finish answering this question real quick. Yeah, so yeah, we're essentially, short answer, Justin, is we're assuming that 2 has to wait. 2 cannot immediately execute B. Like that's just something I'm assuming. There's some sort of data dependency. Okay, yeah. So but yeah, so for Christopher's question, this is just an example, right? Normally you're given a sequence of instructions or something and you have to produce this, but you have to follow rules, right? If let's say you had 3 instructions that looked like this, and I'll again look at some specific examples with a specific pipeline later, so that'll hopefully help clear things up. But here you want to look at the dependencies, see how they're going, see if you ever have to wait at any point in time, and then make the decision about when 3 can get started, for instance. So here, maybe you looked at instruction 1 and 2 and you said, okay, well, they're going to execute like this. When can 3 start? Well, 3 can't start here for the reason that I just said. So 3 would have to start here, and then you'd keep going, right? 3 may be using B, then D, and then instruction 4. You know, instruction 4 can start here, and then maybe go here. You know, however your instructions end up doing, that's what you like. That's essentially, yeah, whatever your instructions are doing is how you need to fill up the schedule. You just need to make sure you're following the rules. Hopefully that answers your question. Okay, yeah. So next question: if C was execute and they took longer sort of blocks of time to execute, that's when we would slice up block to. Okay, so I'm going to do my best to make sure that time-based questions don't appear on any sort of questions, because I don't think they're very good questions. So the way that I'm doing it with cycles is how computers actually work. Computer at the start of one cycle decides what to do, and then the cycle occurs and it does that thing. So if it was to take multiple longer blocks of time, then I would just say that unit C was going to take 2 cycles. So what that would mean is, let's say actually, let me erase some of this stuff here. It's going to be a little bit nasty, but oh well. So let's say instead instruction 1 here was taking two cycles of time. So it's going to take up this whole time right here. Where's that? Okay. So instruction 1 is taking all of that time here and then up here. So now again, we said we had a dependency between instruction 2 executing in C, right? So this is essentially 2 units of time. So instruction 1 takes up 2 cycles. So here now 2 would have to wait till here, and what this would look like is essentially this, and 3 would only start here. So what this would look like is at this point, during this cycle right here, or actually at the start of this cycle, we're just about to execute 2 in A, and we're just about to execute 1 in B. So then we go ahead and do that cycle. So now we're in the middle of here. So now 2 is in here, 1 is in here, and then at the end of the cycle, 2 ends up here, and 1 ends up here. So then the next thing that happens is, well, 2 has to wait to execute in B. So 1's going to go ahead and start executing in C. And we're going to progress forward a cycle. And 1's just going to stay in C because it's still processing. And then over here, finally, 1's going to move on to the next thing. And then things can progress behind it. So now that 1 is right here, 2 can go ahead and get started in B. So the next cycle, the next instruction, during the next cycle, they would be here, and then they would just progress forward. So all that's going on is, if there is a longer amount of time, you really shouldn't have to subdivide. You should just take up more blocks. So here, one instruction, this unit here taking 2 cycles, it just means that the instruction is going to be staying in this unit here for a little bit longer, and that things behind them can't progress forward until this is done. So the whole point of a cycle is that a cycle is the atomic amount of time that a CPU can do anything in. So nothing can be shorter than a cycle, because, I mean, that's the whole point, is that a cycle is one step in time for the CPU. You know, maybe that cycle takes 100 nanoseconds or 50 nanoseconds. Essentially, I'll try to make sure that on any sort of test they get reworded to cycles, because it's a lot easier to understand what's going on when you're thinking about cycles. I mean, you'll get something similar, but it'll say essentially maybe the time, so the T of Fi will be 1 cycle. T of E2 will be 1 cycle, 2 cycles, or 3 cycles maybe, I don't know, but it'll just be a constant multiple of cycles. Or maybe even the time for F1 will be 2 cycles, and then for each E it might be like 2 cycles, 1 cycle, 3 cycle. Like that sort of thing happens, where maybe that sort of thing can happen, where maybe one of your one of the steps in the pipeline takes 2 cycles, but the other one might only take 1. You know, you'll see a little bit more about that in the actual lab later on, and also I can talk a little bit more about that. But the idea here is you want to do everything in terms of cycles. That makes it a lot easier. So let me see here. So now let me go ahead and work through a more concrete example using the usual pipeline, IF, ID, and so on. So let's see here. I guess I'll just draw out my schedule, start off with. But yeah, just to reiterate, if I wasn't clear, there's going to be questions like that where things take variable amount of times. It's just not going to be specific. Hopefully, will not be specified in times. It will be specified in number of cycles. Okay, so let me quickly pull up something from the slides, just for instance. Just because coming up with a sequence of instructions isn't super easy. At least not a sequence of instructions that's interesting. It's taking a while to load. Sorry about that. Okay, let's see here. So actually, let me I'll leave this up here for doing one of those problems, but I'll start with actually a problem similar to the one that you stated. I'm just going to rephrase it slightly. So here, what I'm going to do is I'm going to say T of F equals 2, T of E I equals 1, 2, 3, 1. Or actually, yeah, let me do this here. So we'll say this is 4, and then so every cycle here now equals 25 nanoseconds. So the fetches all take 4 cycles. The execute here, the first one takes 2 cycles, then 3 cycles, then 5 cycles, then 4 cycles, 3 cycles, 6 cycles. So cycles is just a unit. So here in a cycle is an atomic instruction. It's one sort of execution of the CPU is one cycle. So like in the horizontal architecture or whatever, you have the registers in the ALU. One cycle is the time it takes to take one instruction and process that instruction. And here we're talking about like vertical or horizontal instructions. At this level, when we're talking about pipelining, we start talking about just a little bit more of an abstract instructions. They're not necessarily atomic instructions, but essentially, like, you can think of the reason that it's called a cycle is you have your register, you have the output of your ALU, and you're cycling through, right? The data cycles through, so it's one cycle of the CPU. A cycle, I mean, pretty much the easy way to think about it is the cycle is the throughput, right? Because at the start of every single cycle, things move forward a unit, and you can maybe start a new instruction. So in theory, the throughput is one cycle. And then the latency is just going to be however many units an instruction needs to go through, right? Because, yeah. And I think this wasn't done yet. So 6, and then 3, and then 2. So if I'm doing that, right, so I have my F unit and my E unit, whatever those are, fetch and execute. I'm just going to do this in a little bit more of a free form way. So my first instruction is going to start in the fetch unit, and it's going to take 4 cycles. Then it's going to go ahead and move on to the execute unit and only take 2 cycles. So it's going to go over here, and now we're at 6 cycles total. And then we have the next one. So 2 would go ahead and get started, but 2 is going to go ahead and take 4, cycles inside of this unit here. So I can maybe remove this line here and just say, well, it's going to take 2 here. So now at this point here, it'll go ahead and progress forward. So now we have 3 cycles here. So right around there. So that's 3, and this is timestamp 11. Then we have instruction, not 3, 2. So now 3 will go ahead and get started. It'll finish in the fetch unit at 12 cycles. Then after that, 3 executes for 5 cycles in the E unit. So it'll come up here, and that's just 12 plus 5 is 17. Then we have instruction 4. It'll start it'll start immediately right here, right? So 3 is executing in this unit. We can't possibly start 4 until 3 is done in this unit, right? So 3 is going to happen over here, or 4 in the fetch unit is going to happen over here. That's going to finish at 16 because it takes 4 cycles. So now right here, we can't immediately start instruction 5 because, well, yeah, we can't immediately start instruction 5, or I guess we could. Yeah, we could. So right here at time 16, so at time 16, if we look at our pipeline, it looks like this. T is time of the fetch unit, and the I is just the ith instruction. So the T of Fi is the time for the ith instruction to take in the F unit. So we have this, then we'll have our E unit, and then we have another, one of these gates, and then the F unit. So right at time 16, 3 is currently in the F unit, and 4 just finished in the E unit, right? So 4 obviously can't start in the fetch unit because 3 is using the fetch unit, but 5 can actually start being executed. So 5 can start being executed because what's going to happen is that 5 doesn't need to come here the next cycle, right? So this is at time 16. On the next cycle, cycle number 17, right? Well, 4 can just stand right here, and 3 is going to go ahead and finish, right? So that's right here. So at this timestamp here, that's going to happen. Well, 5 can be processing in E because it's just going to be processing, right? So it's time 16. This would go up to time number 20. So 4 is sort of waiting right here to execute an F, and 5 is actively executing an E because nothing else is using it. So it can go ahead and start using it. Then at cycle, so then at 17, at 17, 4 would start using this fetch unit here. It would come in here. So this is at cycle 17. So 4 comes right here, and that takes 4, so that'll come up to 21. So right here, so we're at time number 17 right now. If we go to time 18, nothing's changed. 19, 20. So at 20, 5 is done. It's going to be right here. And 4 is not done, so it's going to be waiting right here. And then at the same time here, 6 can go ahead and start because 6 can use the execute unit while 5 is waiting. So 6 can go ahead and start here. So that's 4 nanoseconds later. That's 24. Or sorry, 4 cycles later. It's 24. They do have these backwards. Yeah, there we go. So yeah, this is it's the fault of the way the problem is stated. TFI equals 4. That means every instruction has to take 4 cycles in the fetch unit. This here means instruction 1 takes 2 cycles in the first, 2 cycles in the execute. The second instruction takes 3 cycles in the execute. The third instruction uses 5 cycles in the execute, and so on. It should probably just be laid out in a table, which actually I'm going to do. So we have the instruction number, time for FI, and time for EI. Really, this is a much better way to lay it out. So we have instruction 1 is for 2. Instruction 2 is for 3. Instruction 3 is for 5, and so on. Okay, yeah. So at time 21, let's see. So at time 20, exactly at the start of cycle 20, we're right here because 5 just finished. And then right as we start cycle number 20, 6 moves into the fetch unit. 5 is just going to kind of sit here because it can't start in the execute unit because 4 is still executing in the execute unit. But at the start, right when cycle 21 hits, 4 is done, so it moves on. And 5 can go ahead and move on to the execute unit. So 5 would actually go ahead and start right here. And instruction 5, so 1, 2, 3, 4, 5 is going to take 3. So that's actually just going to come up right to here. Draw that a little bit better. 5 is going to come right up to here. And so for cycles 21, then 22, then 23, it's just going to look exactly like this here. Right, 6 is actively fetching, 5 is actively executing. And then right when cycle 24 starts, 5 is done, so it gets out of the pipeline, and 6 would move on to here. So now, the fetch unit is free. So, maybe instruction 7 is just waiting to start right here. So instruction 7 would go ahead and go into the fetch unit. So we would have 7 here. That would take 4 cycles. So this is up to 28. Then we have 6 going into the execute, so that's going to come up here, and 1, 2, 3, 4, 5, 6. So that's going to take 6 cycles. That'll be up to time 30. So then for cycles 24, in cycle during cycle at the start of cycle 24, 7 goes ahead and moves into the fetch, 6 goes ahead and moves into the execute. And then the same thing for cycle 25, 26, 27. Right when 28 hits, 7 moves over to here and is waiting. So now fetch is free, so we can go ahead and start executing instruction 8 right here. And that's going to end up running for 4 cycles. So that's going to come up to 32. And so, so right at the start of 28, or right here, and then 28 starts, 8 goes ahead and moves into the fetch unit. And then that'll be processing. And then 6, right at the start of cycle 30, 6 finishes. So it's going to go ahead and come out of the pipeline. And 7 is going to go ahead and start executing. So we can put 7 right here. And that's, let's see how long. 1, 2, 3, 4, 5, 6, 7. That's 3. That's about that long, I think. So that's going to be up to 33 cycles. And so, so at instruction 30, this is going on. Cycle 30, this is going on. Cycle 31, this is going on. Right at the start of cycle 32, 8 finishes. 7 is still executing. So it executes all the way until the start of cycle 33. Then 7 is done. And 8 can go ahead and start executing. And 8 can execute for 2 cycles up here. So that's going to come up to 35 total cycles. So, 35 cycles, we have 25 nanoseconds per cycle. So if we wanted to compute the total runtime, you're going to end up with 35 times 25. which is 875 if I didn't make a mistake. So total runtime for this program is 875 nanoseconds if you wanted to do that. But, you know, probably can just specify in cycles. It's 35 cycles. And I'm not sure exactly what the answer was for the this problem in the lecture, but yeah, it should be pretty much the same but yeah, when you're thinking about cycles, it allows you to think about where things are in specific units at one times and when things are allowed to change, right? You can't just arbitrarily subdivide a cycle and say, oh, well, right in the middle of a cycle, I'm going to start doing something different, because by definition, the CPU isn't going to change from doing one thing to another thing during a cycle. In reality, modern computers are a little bit more nuanced than that. And also, there's things like a pipeline will actually have 2 execute units, and really it's not just an execute. You might literally just have an adder unit or something like that. You might have 2 of those, or you might have 2 ALU units or something like that. But then it gets a little bit more complicated, because then you have to figure out which one of the 2 units that you want to use, because they're the same unit. You just have 2 of them, so you can do twice as many things. But that's getting ahead of, you know, what we're covering in this class. So yeah, just keep in mind, you can't really subdivide a cycle. That's just how that works. And like if you look up a modern computer and you look at the different instructions, like let's say for x86, the x86 architecture, you'll see that some of the instructions have a latency of half of an instruction. But really all that means is that you can do 2 of them in one cycle, because you have multiple units. So it might seem like the cycles are being subdivided, but they're not. Like that's the whole point, is a cycle is the most primitive subdivision that a CPU works at. And something can change only once every cycle, right? At the start of the cycle, you start doing something, and you're not going to change doing it until the end of the cycle. Any questions on this one right here, this question right here? So really handling instructions staying in a unit for a little bit longer is just as simple as just assuming that it's going to be in there for multiple cycles, and that the things behind it can't just push through it. So, well, here the throughput's a little bit weird. So the throughput of this pipeline is a little bit hard to say, mostly because, I mean, the throughput and latency, that's more just talking very, very primitively about pipelines. As soon as you start looking at examples, the concepts of latency and throughput sort of start to break down, because the latency and throughput are going to be different for every instruction. Like, for instance, instruction 1 has a latency of 6 cycles, right? Because from the absolute start of instruction 1 to the absolute end of instruction 1 takes 6 cycles. However, instruction 2 has a throughput of, or sorry, a latency of 7 cycles, because it takes 4 here and 3 up here. And you don't really compute gaps like this. So if you have instruction 4 here and 4 here with this gap, you wouldn't consider this gap in the latency. For the throughput, however, it depends. I mean, in some sense, you could say the throughput is 4, because every 4 cycles you start a new instruction. Right? The whole idea behind the throughput is how quickly can you give this CPU instructions. Latency is how long does those instructions take to finish, right? And the idea is that with the pipeline, you might have instructions going on at the same time. Well, I mean, that's sort of the whole point of the pipeline, is you have multiple instructions going on at the same time. And so the latency and throughput are different. If you don't have a pipeline, latency and throughput are identical, because, well, you have to wait till the instruction finishes to be able to execute the new one, right? If you have just like one unit, you'll have instruction 1, then instruction 2. So whatever this unit of time is how long it takes for instruction 1 to finish, and it's also the amount of time that you have to take to start a new instruction. If you are asked sort of like throughput and latency questions are going to be relatively basic. You're not going to really have an example like this if you even have a latency and throughput question. Those are just sort of, well, yeah, you could maybe say, oh, the average latency of the computer is this, right? You can definitely do that, and you could also say that for the throughput. Say the average throughput is 4 cycles or 100 nanoseconds. But really, we're not necessarily going to ask that. Mostly, like if you've looked at the problems for today, you'll see that you have like the first question is just talking about, well, if you have a CPU with this sort of latency that always happens and this sort of throughput that always happens, how long would it take to execute this many instructions? Yeah, like if you like look up the actual set of like the actual instruction set for x86 or something, the throughput and latency for every single instruction is different, because some instructions take more than 1 cycles. Sometimes you can do multiple of that instruction in the same cycle, and so you can't really just describe the latency and throughput of a CPU itself. But at least for a very basic idea, I mean, it's helpful to think about pipelining in that manner, where you do end up with higher speeds, even though instructions take longer to execute. Okay, so I'm going to go over one last example here with interleaving. So to cover that. So interleaving is actually a feature of the memory. Actually, let me remove this stuff here. It does deal heavily with how the pipeline can run, but that's something to keep in mind, is that it's not the pipeline that is interleaved, it is the memory that is interleaved. And the default, essentially, is one-way interleaving, not three-way or however many way. Sort of, if you were to just naively make memory, it's just naturally going to be one-way interleaved. You have to explicitly design it to be interleaved in a higher amount. And, in reality, essentially, all memory is interleaved at a higher amount. And I think it's not even, it depends on the memory that you're using, but there's other technologies other than interleaving that essentially allow you to perform multiple reads or multiple writes simultaneously. Interleaving is one of those methods that allows you to increase the number of memory instructions that you're processing simultaneously. So let's say we have this pipeline here where the ST unit, the LD unit, and the IF unit are all using the memory. And let me find a sequence of instructions to do. Let's say, I'll save this one right here. So the instructions here are going to be LD, R1, 100, R0. LD, R2, 200, R0. And then add R2, R2, R1. And then ST, 200, R0, R1. Actually, I'm just gonna change this to R2. So just because this is actually a fairly realistic code. This is fairly realistic code. So if, let's say, you have an int x and an int y, and you're trying to do y plus equals x, naively, this is what your code would translate to, because y and x aren't actually going to be stored in registers. They're going to be stored in memory. So here, this is maybe I guess, yeah, 100 R0, that would be where x is. 200 R0, that'd be where y is. So what we're going to do is we're going to first take x out of the main memory, put it into a register, take y out of the main memory, put it into register. then add y plus x together, store that into R2, and then we're going to take that value and store it back in location y in the main memory. So this is very, very realistic code. If you compile C without optimizations, it'll look like this. So first thing here is figure out your dependencies. It's always important to do. So I'll go ahead and number these instructions so we can do that a little bit more easy. So what are the dependencies? So 1 doesn't depend on anything, right? Because it's the first instruction. Well, technically it wouldn't be, but we're just going to assume here that it doesn't have any dependencies. So 2, well, it doesn't have any dependencies, right? It accesses a different memory location and a different register than this instruction. So there's clearly no dependencies. 3, well, it uses both R2 and R1. So we actually have, and we're going to be using R2 and R1 inside of the execute unit, right? Because that's when we're going to add them together. So we have that 3 execute depends both on, well, here, this is going to be a load operation, right? So it's going to depend on the load for 1, so 1 load, and it's also going to depend on 2 load, right? Because we need both of these loads to finish before we can go ahead and do the add, because otherwise we don't even have the things that we're trying to add together. That sort of defeats the purpose. So that's all the dependencies, right? And we're also overriding R2. So technically there's a dependency between these two here, but the fact that we have 3 execute depending on 2 load means that 3 execute also depends on, that's the same dependency here, right? Because we're going to be modifying R2 during the execute unit, and we're also modifying R2 during the load unit. So that dependency is already written down. Right, because here we're writing R2, we're writing R2, so technically there's a dependency there, but we've already covered it, right? It's this dependency right here. Okay, so now we have instruction 4. Instruction 4, what it's going to do is it's going to use R2, right? So we just computed R2 and we're going to use it again. And this is going to happen in the store unit of 4. So we have 4 store is going to depend on the execute of 3, right? Because here, it's during the execute stage that we're going to compute what R2 is. And then it's during the store stage that we're going to take R2 and store it in the main memory. So we need to have that. And then there's also technically a dependency between the load for 2. So let's see, the store for 4 depends on the load for 2 because, well, here we're going to be reading this value from main memory. And here we're overwriting it. So we need to make sure that happens the right order. However, if you notice here, 4 store depends on 3 execute, and 3 execute depends on 2 load. So we don't actually need to write this one down because it's already sort of implicitly defined by these dependencies, right? If 4 depends on 3 and 3 depends on 2, then 4 also depends on 2. We don't have to write both of those. That's just pointless. So we know that even though this is a dependency, we don't really need to care. We don't care about it because it's already going to get taken care of by these dependencies. So these are all our dependencies. 3 execute has to happen after the load for 1 and the load for 2. And the store for 4 has to happen after the execute for 3. Are there any questions on the dependency stuff here? Either about how I got certain dependencies or about why I'm not including other dependencies. So 100R0, what this means, so you have your registers, right? You have register R0, it holds a value. So we're over here. Let's say it holds, I don't know, 24, or actually 28. So what this here tells you is you also have your main memory. Over here, so these are your registers. What this tells you is it says, okay, look at the value in register R0. We're going to then add 100 to that. That's going to be 128. So then we're going to take the value of 128. We're going to go into the main memory to location 128. And maybe right here, there's the value 49 in main memory. we're going to take this value here, right? What this says here is add 100 to whatever R0 is, and that's the memory location we're going to go to. So this load R1 100 R0, what it's going to do is it's going to, if I write that out fully right here, so this is what this says right here is, okay, so we're going to look for this memory location. What is it? So R0 is 28. So we add 100 to that because that's what the offset is. So we're adding 100, we get 128. Because we're doing a load, we're then going to go to the memory in that location. We're going to get this value, and it says we're going to load this into this. So we're now going to take the value of 49, and we're going to put it in register R1. So that's exactly what this operation does, is it takes R0, adds 100 to it, goes to that memory location, gets the value of the data in that at that memory location, and then puts it into register R1. It's definitely not a stupid question. So the reason that you might want to do this, the reason you would want to do this instead of something else is, well, what if you don't know what R0 is? Right? So like if let's say you were specifically accessing a memory location, like let's say you're accessing, maybe you have an int x, and that int x is stored at exactly a memory location 256. Right? There's no reason to have it referenced in terms of register. Like if you know your int x is at location 256, just access that. However, for something like an array, the way that arrays work is it just allocates a contiguous block of memory. So like essentially you might have it where location 128 is, location 28 is the start of your array, and you have a value here, and then you have location 32. So we're skipping by bytes here because byte addressing. And so the first location, the first element of the array would be here, the second element would be here, the third element would be here, and so on. And this right here would be the 25th element of the array, because what we're saying is we're going an offset of 100. If you divide 100 by 4, that's 25. So that's 25 spaces after the start of the array, and the start of array we just store as R0. So this is basically, this could be saying get the 25th element of my array. But essentially it's most of the time you don't want to just use absolute locations. You don't want to say I want to go to memory location 128. Usually what happens is you have some sort of scope that tells you where in the memory you should be looking, and then you want to offset based off of like a base value. So maybe at somewhere in one of your registers is holding the value 256, and what that's telling you maybe is that all of your variables are going to be between location 256 and 512. But you don't necessarily know that. All you know is that you have this 256 byte block of memory allocated somewhere, and you have the start of it stored in R0, but you don't necessarily know what that is. So that's where the offset come in handy. And to some extent, one of the later labs, actually on Tuesday, I believe, you're going to be doing some memory stuff in VML, and that'll hopefully help with understanding how memory works and how you interact with it. Okay, so now we want to go ahead and figure out what units all of these use. So, as usual, all of these are going to use IF and ID, so I'm not even going to mention those. So instruction 1 here, well, it's going to fetch, decode, and then it's just a load operation. So 1 is going to use just a load. 2 here is also just a load. 3 is just execute. Okay. 3 is just going to be the execute, and then 4 is just a store. And in reality, this is actually how most operations in a CPU sort of pan out. Usually it'll sort of use the fetch and decode stages, and then only one of the other stages. It usually doesn't use more than one. Some more complicated instructions do, but most of the time your code is going to get broken down into such a way that essentially every instruction is going to just use one unit, and that way you end up with really, really nice parallelism, unless there's a data dependency. But for the most part, that makes it so that things can execute. Like if you have to use all 5 units, that's a pretty expensive operation. And it's usually going to block something else up, especially if there's a data dependency. But because we can skip forward units, essentially it's going to be if id skip to the unit you need, if id skip to the unit you need. And because of that, you're pretty much never going to have to stop. Like all of this is going to just work out fine. And we'll see that. And here, I'm also just assuming that every single unit takes 1 cycle, just for simplicity. We'll go ahead and draw out grid here. Actually, I should probably wait a second. So we'll start with instruction 1. So instruction 1 is going to go ahead and start at the beginning of the pipeline. And so now here are these blocks I'm using as exactly 1 cycle. So it's going to start in the fetch. It's going to go ahead and decode. And then it's just going to go ahead straight to the load unit and execute that. Easy. So now we can start instruction 2 right here. Right? So we do 1 and 2. So right here we fetch the instruction. And then, well, maybe we have to wait, but we don't, right? So we can go ahead and move on to here. And then after this, well, 1, at the end of this cycle here, 1's done, 1's gone, 1's out of the pipeline entirely because it finished what it needed to and it doesn't need to do anything else. So it's done. So now 2 can go ahead and just jump straight to the load unit, right? Well, here it's not really jumping, but it's just going to go directly to the load unit. And so the way that I worked out the dependencies is I looked at 1 and see if it depended on anything above it. I looked at 2 and see if it had any dependencies above it, 3 above it, and I write these out like this. And what helps with this is that whenever you're putting an instruction, you just want to see if that instruction appears on this side here. So instruction 1 and 2 are not dependent on anything else, so we can just schedule them no problem, right? There's not going to be any sort of issues. It's only when I go ahead and try to schedule instruction 3 that I might have to delay something at some point. So when we fetch the instruction, we don't know what 3 is doing, so we don't know there's a dependency. We'll go ahead and decode it because, again, we don't quite know there's a dependency. But right at this point right here, we realize that there was a dependency between the execute for 3 and the load for 2. However, the load for 2 is done, right? Like once we decode this, we would have said, oh, okay, well, there's actually a dependency between 3 and 2, but it doesn't matter because 2 is already done. So we can go ahead and just move 3 to the execute unit. And also, it's the load for 1 is clearly done. It's over here. So we can go ahead and just skip 3 straight to the execute unit. I do see someone type a question, so I'll go ahead and wait for that. Oh, and I should probably make a note that I'm doing two-way interleaving right now. So right now, if you look at any period in time, there's no more than 2 units using a memory unit, or 2 instructions using a memory unit simultaneously. So right here, and what I like to do as I'm working through this is just write down how many units are using memory at a time. Just makes it's very easy to see like so right here on this first timestamp and during this first cycle, only 1 unit is using memory, right? This IF unit here is using memory. Then during the second stage, again, it's only 1 unit. Then during this stage here, we have something in IF and something in LD, so we're using 2 units, but we're using two-way interleaving right now, so that's fine. Then we don't really know about these 2 because we might put something here. So the next instruction here, so well, just to point out here again, so we have this dependency here. That's just these 2, or sorry, not those 2, these 2, right? The execute for 3 has to happen after the load for 1, and it also has to happen after the load for 2, which, you know, that happens, right? These are all happening in the right order. So these dependencies here are handled. I'll go ahead and put a check mark. So once we've handled a dependency and we no longer have to worry about it, we're done. We don't actually need to pay attention to it. So then 4, well, 4 we have to fetch it and decode it before we can figure out if it has any dependencies. So we can go ahead and fetch it and decode it here. So for here, I put an asterisk next to them, and you'll be told explicitly in a problem which units use memory. That's not really something that you would know. With this pipeline, specifically, these are the units that use memory. The fetch, right, because it's fetching the instruction from the memory. The load, loading something from memory, and storing something to memory. So these are the units using the memory. But generally, even with this pipeline, we'll say specifically IFLD and ST are using memory. And yeah, it's usually helpful to put a star there, just make it easy for you to figure it out. Yeah, so we'll go ahead and fetch and decode instruction 4. So now we can go ahead and handle the dependencies, because, I mean, how are we supposed to handle it, know what dependencies 4 has until it's been fetched and decoded? We can't really do that. So now we have that the store for 4 is dependent on the execute for 3. Well, right here, when we finish decoding 4 and we know exactly what the dependencies are, right? We know that there's a dependency between, we know what this dependency is, right? And keep in mind that we had to figure these out manually, but there's a circuit on the CPU that can do this, right? That'll look at 2 instructions and figure out exactly what the dependencies are. It's kind of crazy, but yeah, there's literally just a circuit that's going to do that. So right when it finishes decoding 4, it knows exactly what these cycles are. After 2. So all he means is you cannot execute 3 at the same time that you're loading 2. So you have to wait for 2 to finish loading before you can start executing 3. So that's what he means. You have to wait 1 cycle, right? You can't be loading and executing with the same data at the same time. Yeah, so that's all I mean. Like even though like the load is only guaranteed to be completely done here, and so if you need to use that result, well, you have to do it the next cycle. You can't somehow assume that's going to be able to load and execute in the right order during the same cycle, right? That's not necessarily guaranteed, but at the end of a cycle, it's guaranteed to be done, just by definition. At least for this problem here. So yeah, we go ahead and fetch decode 4. We know that this is a dependency, but we know that if we start the store here immediately, well, you know, the store for 4 happens after the execute for 3, right? It happens in order and time. So that means it's fine. It can go ahead and do that. There's no problem. So that would be it, right? In this case, even though there were dependencies, and there's only 2-way interleaving, we were able to execute each instruction just back to back to back. No problem. So, you know, data dependencies can cause issues. They can cause the notion of a hazard. And those hazards appear whenever you have to wait, right? That's a hazard, right? Because that causes an issue. But these are just dependencies. And sometimes the CPU can just run those without even caring, right? Sometimes it doesn't matter. It'll just be able to do it. And like with the example that I did at the beginning, the reason that the first one is, the reason function 2 is faster is essentially because there's multiple adders. There's multiple ALUs inside of actual CPUs. And so it's able to execute multiple of those addition or those weird addition or subtraction operations simultaneously. Like it can process multiple of those at a time. But with the other one, it has to wait every single time. So even though it's going to be scheduled in the pipeline back to back to back, you're only going to be making use of, let's say, one of those LUs instead of multiple. But again, that's getting a little bit more complex than we cover in this class. So what do you mean you program them out of order? Because so the compiler isn't going to necessarily intelligently be able to figure out what you're trying to program. No, the CPU, like if you swap the order of these instructions, it'll just do that in that order, right? Because keep in mind, all the registers have something in them. Maybe you don't know what it is, like maybe it was a function that you called that used the registers. There's still something in it, and so you can still do literally any operation. You can read from anywhere in memory, unless the operating system tells you not to or something like that. But you can use any registers. You can do literally what you want. At the hardware level, when you're programming with these instructions, the CPU will let you do basically anything. It's really just once you, and the sort of idea is that's why we use programming languages, is because you write in a programming language, and then someone who spent a lot of time figured out how to convert that programming language into these instructions so that they always work and it never breaks. And so that way you don't have to deal with these instructions here and maybe doing something in the wrong order or anything like that. But CPUs will reorder these instructions. This is, again, getting into modern stuff. A CPU might look at these, say, oh, actually, I can do these in a different order. The result will be the same, and I'll be able to do it faster. Again, all in hardware. It's magic. But yeah, okay, so let's go ahead and do this with one-way interleaving. So I'll go ahead and just, I can erase this here. So with one-way interleaving now here, well, actually, let me finish trying this out. So here we're using 2 memory units, here we're using 2 memory units, here we're using none, and here we're using 1 memory unit, right? So here, because we're using 2 memory units, that would be against the rules, right? So for one-way interleaving. So we'll go ahead and draw out a new schedule here. So IF, and the answer here would be 1, 2, 3, 4, 5, 6 cycles. Or maybe if it's 100 nanoseconds per cycle, then that would just be the same as 600 nanoseconds. But really, when on a test, if we ask you how long does it take for this program to execute, we're really asking you to give this table. That's what we want. We don't want to just know how long it took. We want to see like how you worked through how things would be scheduled. So ID, LD, EX, and ST. So now with one-way interleaving, we can only use 1 memory unit at a time. And again, this is due to a limitation of the memory, not due to a limitation of the pipeline. The one-way interleaved memory, that's just the memory saying, okay, well, I can only process 1 memory instruction at a time. So even if you have 2 units trying to use memory at the same time, I'm just not going to allow that, right? That's just not going to work. So these units are still the ones using memory. And so here we already know what uses what units. So we can work through this a little bit faster. So instruction 1 will start here, move here, and then get loaded. And 2 is going to start here, move here, get loaded as well. 3 now, well, 3 can't start here, and the CPU can know that, right? The CPU knows that there's something going on in the load unit. So we can't start 3 here because that would be using 2 memory units. So the CPU is intelligently going to just say, oh, well, I'll just wait. All right, I'll just wait to start executing 3. Well, maybe till the next cycle. So then we would go to the next cycle, and we see 2's already using the load unit. So we can't start 3. So then we'll wait all the way till here. So 3 is going to start here, then it's going to get decoded, and then obviously here, 2 is completely done. We had to wait till 2 finished before we could even start 3 because of the interleaving. So obviously these dependencies here are going to be satisfied. And then we can go ahead and start 4 here. Right? So here there's no memory units getting used, so that's fine. ID is not a memory unit, so we can go ahead and use that. And then over here, we can go ahead and schedule for an ST. So now it'll take 1, 2, 3, 4, 5, 6, 7, 8. 8 cycles, or maybe 800 nanoseconds if each cycle is 100 nanoseconds. So the first question is, does every instruction use IF and ID in the architecture of this problem? Yes. So here, the pipeline is split up into these 5 stages. The first stage is fetch the instruction from main memory. That just, so essentially all your programs, the programs exist in the main memory. So in order to be able to do anything, what you have to do is you have to have the CPU know how to go to somewhere in the main memory, grab that information, then execute the instruction. And so this first step here is that the first step here is get the instruction from main memory. Then it has to decode that. So then it has to figure out what that instruction is doing, what the dependencies are with any of the instructions that are currently executing, so on. Like it just figures out what the instruction needs to do and whether or not it needs to wait to start executing that instruction or something like that. So every instruction needs to be fetched and decoded, but you can't handle dependencies until it's been decoded, because otherwise you have no clue what the instruction is. Then you have load, execute, store. Maybe you need to load something from main memory, some data. Maybe you need to just execute some stuff on that, or maybe you need to store. So yeah, and in this case, every single instruction needs to do IF and ID, because otherwise you don't even know what the instruction is. All right, the other one is, so the one-way, two-way, etc. is the amount of allowed memory access, like the amount of memory you can access, or amount of memory accesses you can do in a single cycle. Yes, essentially, right? So one-way interleaving. Well, here if we look at it, there's only one unit using memory. Here there's only one using memory, and only one. Here only one. Here no units, and then here one. And yeah, so one-way interleaving means you can't do two or more than one memory transaction in a single cycle. Any other questions on this? Yeah, so the one sort of pipeline that, like this pipeline right here that I'm talking about, you sort of want to memorize, because we might just say, okay, well, you have the pipeline with IF, ID, LD, EX, ST, and then stuff, right? You should know how this pipeline works for a test. If we talk about any other pipeline, we'll make it clear how it works. But if we talk about specifically this one, it works exactly the same way that it will for every problem. So every instruction has to use IFID. Load is only used when you're getting something out of memory. Execute is used when you're doing register to register operations or addition or any sort of operation. ST is used when you're putting something back into memory. And that's if ever you see this pipeline here, and again, you might see it under a different name. Instead of LD, you might see OF. Instead of EX, you might see OE. Instead of ST, you might see OS. But they're all the same thing. We'll try to be consistent with this notation here. All right. Any other questions on this? So in this pipeline here, in this CPU, yes. So here, well, yeah. So here, yeah, the throughput for operation 1 would be 1 cycle, and in this case, in this CPU, the throughput for the whole CPU is 1 cycle, because here everything just takes 1 cycle in every unit, just as a simplification. So here the throughput is one cycle. The latency for operation 1 is 3. Or 300 nanoseconds, or 3 cycles, because again it takes 3 full cycles for that to finish. And in fact, that's really for all these instructions here, the throughput is 1 and the latency is 3, because well, it takes 3 cycles to run every instruction here. And the same goes for here. Like, even though we had this bubble here, that's not really incorporated into the latency, unless it always occurs or something like that. But again, you don't have to worry too much about throughput and latency when you're dealing with an actual specific example, because again, it gets really, really complicated. But yes, you are correct there. Any other questions before we go ahead and start working on the questions? All right.